Good morning, everyone. Welcome to our first seminar of ISHRAE. As you all know, that MEP Space Planning is one of the crucial design aspects once you start going for higher scale projects. Of course, for small scale projects also, but you guys will be actually considering this design aspect in your AD projects, in your thesis, and henceforward in your career. So that is why we have specially called for a consultant who is actually having a large experience of 24 plus years, who has worked in MEP space planning for hospitality projects, commercial projects, and many other kinds of projects. So I welcome Mr. Sooraj Nair and hand over to him. After the lecture, please you are free to ask any questions related to whatever he has covered, or even if something you have any other doubts related to MEP planning, please feel free to ask questions. Okay, thank you.
Thank you so much. Thank you. Am I audible, or is this better this way, or is it better this way? Fine. So first thing I would thank IES College and also my ISHRAE chapter to give me the opportunity that I can put my thoughts to the future minds. Right? We call the architects as the captain of the ship. Any engineering or structural consultant always look ahead to the architect to give the direction, the form and shape of the vision of a developer. So you understand the developer's consideration and you give it a form, you give a shape to the entire thought process of a developer. And when you form a building, you need some support services in terms of how the engineering gets fit into it, how the structure gets fit. So I am just putting up a perception across and just putting it together into a sort of a presentation, trying to streamline the thought process of say called sustainable engineering design, in which MEP is a part, but MEP can always be only useful if you design the project in a sustainable way. So the buzzword going across in this industry is sustainability, which actually comes from the point where you sow the seed of the building in terms of design. So my topic for the next 1 hour, where I hope you don't get bored by the big lectures. I'll have some graphics to put it through you so that it keeps it little interesting. And then we'll see, we'll have some discussions across in the question answer sessions, and we'll try to give you the industry experience. So are we ready, or we need to wait for some time? Yeah, okay, right. So with that keynote, we would start the presentation on the services. What you see across, I have tried to stress upon a little bit more about tall buildings, because where you are working on projects, particularly in this part of the world, in metro cities, it's all about being taller and taller, because you have less amount of space and you have to consume the FSI that is given for your development. And in an urban city where you have lesser space, you get larger FSIs to build, but it should be efficiently built. That's the intent of design. I had the experience of working in Middle East also. So you can see the extreme right corner is the Burj Khalifa, which is an 828-meter tall building. I didn't design Burj Khalifa services, but I have had the experience of being there. I've seen what the systems are there. In Middle East, I worked on a 365-meter tall building. It's a hospitality. When you say hospitality, it's about hotel projects. So it's a 1600 key JW Marquee hotel, which I was a construction manager over there. So I had the experience of engaging from getting the basement raft done to the building lightning mast also getting commissioned. So that experience pulled me back into our country back in 2011, where our country was trying to go taller and taller, because considering where we had space. And that experience really helped. So I've just pulled out some pictures just to give you a little references. The buildings over a period are only going to get taller, because this area that is available is going to get squeezed in with respect to the space that we have. Okay, that's about me. So I'm Sooraj Nair. I'm the founder director of Groom Designs. Groom Designs is an engineering consulting firm. Not going to market my company, but we need to understand that as a consultant, we are also thinking about sustainability. And Groom, as a name implies, it's being green. It's a German inspiration of being green. So whatever the DNA of the design of an MEP comes into picture, it's all about sustainability driven thought process. I have 25 plus years of experience in this industry. Started from 97 after passing out from Sardar Vallabhbhai Patel College of Engineering. And from 97 onwards, I am working in various thought processes of engineering. I have been a contractor's designer to a consultant, and I've been to Middle East where I've actually built buildings. And I've started, come back, I've started my own. So it has given a various exposure for me to really put buildable designs. I would say it's a buildable design. It's not a theoretical design. So what I need to tell you forward in the next 1 hour session is something about engineering which is buildable. Okay, this slide is something which compares a human body to the formation of the building in terms of whole life cycle of the building. So if you see the body, as we as a human would need a shelter, which is what you as an architect would like to define. It needs the water, it needs the food processing requirement, it needs oxygen, it needs sunlight. Same if you compare that to a building. Building is an extension of a human body. If you treat your building as an extension of a human body, you will design it right. Otherwise, you'll make it as a concrete mass or a glass building. Should not be the case. The design should be breathable, livable. So if you compare both the aspects of a building and a human body, when you do a site selection, the site should be selected with consideration of, I think it's not visible here, there's a water column here. The building should have water to be received. So it's not visible over here. And it needs electrical energy, which is like your food processing for a human body. Water is needed in all source for the human body. So it needs a processing of the body to happen with the food. That process is your electrical energy, which is powering up your building. It needs a good indoor air quality because you need to breathe. You're spending 2/3 of your life inside buildings now. Right? Whether it's your home or whether it's your office or what, but you spend 2/3 of your life within houses, within buildings. So the quality of the air that comes into the building is very, very important, the fresh air content. And you cannot be boxed in a metal box which has got no exposure to outside. That's why you need to have daylighting. That's why you get connected visually to the outside. So the daylighting and sunlight is what works together. So for a human body, if all those segments work together and that's how you be healthy, same case for the building. If all these elements work in a synergy together, that's how you design a good, efficient building that is sustainable for a longer period of time. But it says it is dependent on energy, correct? Electricity is something very, very critical. So in a country where there is shortage of electricity and over a period of time with the way our population is getting expanding to enormous numbers, the demand on the construction of buildings or usage will be still further increasing. That means it is going to put a strain on the existing infrastructure of the nation. That's the reason the stress upon electrical systems are very, very critical, and the design of your building should come into picture that it should consume less. If it consumes less, you will produce less. If you produce less, your strain on the natural resources of production will come down. And that should be the intent, and that is basically the benchmark how to set a sustainable engineering design. So it's a synergy between an architect and an MEP designer to work together, where we call it a sustainable engineering. It's not just building mass and not about just pumping in equipments to make a system work. So keyword saying, if you want to consume less, you will produce less. So get a design which defines the consumption to be less in terms of usage. So that's something that we would address as we move forward. Ultimately, it takes you the well-being of the life. Okay, this gives you a little idea what happened in the age where we didn't have systems in place, where we used to store in our olden, maybe just about 40-50 years back, even in the villages, we used to store in wooden compartments in our grandmother's house. All our food was stored in a chest, in a wooden chest. It was still sustainable. Even the perishable food used to be saved. What do we do now? We put them all in our fridge. Consumes electricity, right? As we move forward, we started doing buildings, which is more about glass, trapping the heat and then saying I'm going to treat the heat by doing air conditioning system. Earlier on, the built environment was different. You used to build a building which is suiting the environment. The intent is to find a finer gap, how you can get modernization and also work towards the pre-usage areas. Try to eliminate this. I'm an MEP consultant, I'm saying please eliminate this. Engineering. Why should you want to cool a space if you can make it natural? But practically it may not be possible. So that is something that we will try to bridge and address. People used to do household work, go to do farming, now we do treadmill to make ourselves fit. We used to be fit by doing physically work, right? But now we eliminate that physical work and we say we are going to do a treadmill. Again, to make ourselves fit, we are consuming energy. The stress upon energy is taking you towards a climate change because that's where the entire thought process is now going forward. Again, a little comparison, I'm putting more context into place before we really talk about engineering. If you see the evolution of three perspectives, the disease, the electrical consumption and transportation, that's something which is very, very crucial how it works out. In the early period of our life, where we were living in small huts and mud houses, we were impacted by smallpox. Our transportation was only bullock carts, right? Then we opened the waterways, where the world started getting connected by waterways. Buildings started getting further defined with more mud, cement and stuff like that. The invention of clay came into picture, early 1920s. The travel from various place to the other place, the seaways started getting opened up, so we have raft and ships to come into place. As we move forward in the 1950s onward, we started building concrete buildings with glass, with the invention of tuberculosis, with connectivity from the railway network. What does it state? Then at present, where we are doing all glass buildings, visually, making buildings more looking appealing, because we have a technology to prove that the building can become efficient, and the travel between various parts of the world is because of connectivity to the aeroplanes. You can see what's happening now. The disease for COVID-19 is moved out. We cannot arrest this, but we can probably try to curtail the thought process. There is an interdependency in this thought process that the more the technology advance that we use for, it allows people to communicate freely one with each other. It also gets into transmission of diseases. You have to live by this. In the future, another 50 years down the line, something else will come. But the building should be able to sustain all these thought processes. But this is just a journey in which it states how the interrelationship between building a building, the transport and the disease becomes a part of our life. And we as solution providers need to start looking into these contexts that, like we are now doing, right? Post-COVID, we are always doing sort of a lot of interaction through Zoom calls, Zoom meetings and stuff. So less amount of connectivity, physical appearances and stuff like that. So just to put a context of it, why sustainable engineering comes into picture around it. Okay, so in the previous designs where we used to work on, we used to get our energy coming from coal. I'm getting the basics and then we'll come into the thought process. When you burn the coal, for 1 kilowatt of consumption, we emit out carbon dioxide about 921 grams of carbon dioxide. You can imagine. Then we started getting cogeneration. That means whatever coal I was heating up, there's a heat that comes away, I can convert it into energy. So it reduces the consumption. Then we got natural gas. We started using natural gas, it is taken down the reduction further. Then we have geothermal. That means there is a mass within our earth which can be used to either take heat or give back the heat. That is further reduced. The intention is now to click to this space where the consumption patterns is getting produced in your own space. That means I have started using renewable energy as my thought process into the building. So the building should be able to encompass renewable energies, and that's how your reduction of power comes into picture. The world is now trying to look at. Developed countries have already reached there. We are shifting from here to there in a transition period. It might take maybe a couple of more decades. we have very few net zero buildings which say that they produce your own, own energy. And it is still in a pilot project. It is not in a commercial way that we can really do net zero. But it is important that we should look at towards how we do net zero. So when you really start building the electrical requirement, you start emitting carbon dioxide across the entire earth concentration. And what it really speaks about, I think there's an issue with how things are not really looking well over there, looks like. Okay, fair enough. It forms a sort of a gaseous perspective around the building. When the carbon dioxide that you are putting outside to the earth, because you are generating all the energy from various sources that you have, and I spoke about the various terminologies of carbon dioxide emission, the various source that get commits creates a layer which is trapping the heat around the earth, which will lead to an additional global warming temperature, and we start again consuming energy to make things function for you. So it's a vicious cycle. More the carbon emissions keep on happening around the building, the more the rising temperature, more the system strain on producing systems for air conditioning, for design, which will keep the building cooler. So that's where the vicious cycle keeps on coming to. And that's what we're saying, that we should try designing a building coming to as close to, I'm leaving away this part, we talk about net zero. I'm touching upon this base about net zero. What does net zero? Because you will be getting exposed to buildings which say, is it practically possible to make a net zero building? Net zero means whatever you're consuming should be produced or offsetted somewhere. That's net zero. So if I'm consuming, say, this hall, 1,000 square feet hall, with all this air conditioning system in place, is consuming maybe 5 kilowatt of electrical power, then the 5 kilowatt should be generated on top of this building somewhere, not putting a strain on my electrical supply, and that can be generated either by a solar or if you have a wind, because you're close to the sea if possible. But there are efficiency ratios for various perspectives. Solar is much more usable in India considering we have good radiation, and wind would be subjective depending on where the velocities should come. The conversion of wind energy to electricity is little sparse. You need to be high to the high ranges for you to generate that kind of stuff. So intent is, over the year, what you can consume should be produced. That is how you become net zero. I'm coming back to the same topic that I spoke about in the start. Why consume why produce when you can consume less? So consumption, if you can reduce by a good design, will help you to put a system which is of a lesser capacity, which will be placed within your building, it will take up less space within your building, and that's what the entire discussion will come up of how the planning of the services, the percentage areas that would come. So if you consume less, you produce less, and if you produce less, your generation is also less. That's the intent. So think about production, consumption and generation. These three elements, if you can tackle around the building, that will help you to think about how. So this speaks about, I don't know why it's not visible. The point zero is about net zero energy. So it talks about, so it talks about reduced energy consumption. We have a high performance envelope. We will design the envelope which is really high performance. It is not allowing heat to come inside, and appropriately designed systems, the MEP systems are designed equivalent to that, and we have on-site energy production. So some of the visuals are not much clear here, but that's okay. And then we keep on monitoring it, because every technology over a period is going to only evolve. So we can improve the technology by monitoring it. Okay, so now it comes to the fundamentals of what the building is supposed to be. Right. So if you look at the fundamentals, I'm going to touch upon only the fundamentals. We're talking about the heat, the energy, heat, air conditioning, daylight, sight and water. These are major perspectives that a building should be able to work around. I need energy, there's going to be heat on the building because based on the location where it is. Then I need to cool it, or I need to give provision for cooling. I need daylight to come in so that I don't feel trapped in a building like that. The site is accordingly selected with all these parameters, and I need water. The site is also very critical where you choose it, whether it is a brownfield site, whether it's a greenfield site, whether you're doing a redevelopment. So all the consideration would come into picture for the site where the building is getting placed. Okay, some example about what it means, electricals across. I'm just skipping this, but it's just an idea for you what we need to look into. Okay, air conditioning. When we say we are having an air conditioning system, we need to cool a space that we call it tonnage. So when you say 1 TR, these machines probably are 1.5 or 1 TR machines which are put here. So if I am counting them 1, 2, 3, 4, 5 and 6, I have a 6 tons of air conditioning sitting in this building, in this particular. If I could have designed this better or not, that's subjective. But I can start reducing this if I do much more insulation to the building from outside or inside. If I start reducing it, my consumption of this might reduce to say 3 out of the 6, and you start coming down, right? So that's tonnage of refrigeration that comes as air conditioning. Daylighting is something, so it's not been visible much, sorry. Daylighting is something which is very important, and it is basically how much external light is coming within a property and how much you can use for your own lighting purpose. Like today we are in a seminar hall. If you have an opportunity to discuss, we will open up all the window shades, right? You will have light coming inside. What will help? All these lights that you have put artificially can come down. Physically replacing the artificial lighting with an external light which is abundantly available reduces your consumption of your property. But it is subjective to the usage of the space. If you have everything and you start putting daylight, you probably will not be able to engage the conferencing discussion. So every room, every building will have a challenge with respect to how it should be designed. It's not a one-fit solution for all. It is going to be different thought process. But daylighting is something that helps you to connect outside. It helps you to reduce energy in a building which is working on a 7 to 8 hours conventional way. But in a building which works 24/7 where mechanical lighting is necessary, it still gives you a reduction in consumption of power. So that is something that you should always look into. But when you say daylighting, it depends on the window wall ratio that you design, because it depends on the incidence of the angle of light that comes. You can't make a full glass opening and say that I'm making a great daylight. It may only add additional heat to the building because you are trapping the heat, and then you're starting to cooling the plant. So there is a efficiency ratio where we call window wall ratio. In a commercial building, we say it should be less than 50%. So we say 40, 45, 50. That's a window wall ratio that we expect a commercial building to be. Residential buildings, you can always design as per your natural ventilation strategies of the property. But when you do commercial buildings where air conditioning plant rooms are necessary to do the cooling requirement, it comes down to 40 to 45 to 50%. And then the selection of the glass will come into picture. But it is something that speaks about the, so that's what we spoke about, the percentage of glazing, the visual specification of the glazing. So we generally, you have single glaze unit, SGU you call it, you have double glaze unit and a triple glaze unit. Now, there is always a fine line between a double glaze unit and a triple glaze unit. Generally for commercial building, we go with double glaze unit, DGUs, and it has got an air gap, and then you have 2 levels of glass that comes. Triple glaze units will be going towards more where you have acoustical properties to be considered into it. If there is a zone for, if there is a building very close to an airport, you may need to consider the fascia which is on the flight path, probably with a triple glaze unit also. But the fine line between a triple glaze and double glaze is the expense, the cost of a project goes maybe 40 to 50% higher. And single glaze units are generally considered in residential buildings where you are in any case trying to create a naturally ventilated environment. There is no point of living in a space where you are continuously into air conditioned space. But when you come into commercial spaces where you are in a zone where you are not allowed to get movement of air, you feel comfortable when you use an air conditioning. So air conditioning building, very specific, this becomes a very clear requirement. The percentage of glazing, visual specification, how much can you see out to in or in to out, and the glazing height. The glazing height also plays a big difference because the angle at which the light comes in how much we can harvest as daylight is what is critical. So there are something called light shelf that we design which allows light to transmit inside and allows them. So orientation of the building becomes a very critical factor during your initial massing planning of the building. Lux lighting level is very to understand. When we say lighting, what you see here, if the tube light is switched on, it's emitting some lumens. That means it is exiting out some sort of a form of light. But when the light is controlled in an environment, it is called as lux. That means if I push out here and I trap that water into a bucket, that quantum of volume in the bucket is the lux. So you can't over design a building considering I just want to make it absolutely a floodlit stadium. Stadium with a different lux level. That means at the occupied level, what is my visual thought process? How do I see without impairing my vision around it is the lux. But what the light emits is lumens. This is something which is important to understand. Because what happens is, when you do interior designs of spaces and if you start designing for 500, 600 lux of a space, you are going to consume more power because you need to power them additionally. This definition of lux level is based on how you will define the space and do we have a possibility of windows connected to these spaces. So you get a daylight benefit and then you start designing the lux. So that's something as a basic that I thought we should discuss about. Okay, then comes your site selection. Now we have a term we call it in the sustainable engineering, and as you move forward in architecture, in your real learnings of architecture, and when you start getting internship with various architects, we call it as microclimate. When we say microclimate, it's not about the environment, it's actually within an environment and on a site, what additional buffers, measures that you create that will keep the heat island effect of that particular space under control and maybe even lessen the temperature at the ground level. So if you create more vegetation in and around all buildings, vegetation, and you have more about you can say water bodies around it, helping some evaporation to happen, it cools down that particular usage. Now if it cools down, it is also reducing the urban heat island effect, which in turn is going to help the reduction in the loads on the property, which will help the reduction in the MEP size. Ultimately, MEP equipments are for a building usage. I said reduce, consume less, so produce less, so the regeneration becomes less. If we can 3 elements come in, we can also reduce the heat island effect. This becomes a critical factor in terms of understanding. Now, potable water. I'm just taking all fundamentals before we really speak up to the main topic about how the buildings are. When you look at water, you need to understand water because that's there your understanding of your syllabus. We call it potable water. Water that is considered safe to drink. So there is a WHO standard where we say certain parameters and you can drink them. Then we have grey water. So what is grey water? All the wastewater generated in household or office buildings from streams without fecal contaminants. Anything that doesn't get connected to a WC is a grey water. But your process, your washing machines, your wash basins, all those are considered as grey water. Black water is the one that you use for your wash WCs, the closets, the WC closets, which is getting contaminated with human waste, is your black water. So you will always have the design requirement and the guidelines from the municipality says you need to take separate downtakes for a design. That means within the plumbing of your property, you should have a separate downtake for waste, you should have a separate downtake for black water. You may club them at a later stage because when you say black water, it can get clogged because of the quality of the water that is running within that plumbing lines. It can get clogged, so they say the clog should not impact the entire building design. There are systems where we are now working with combinations, where we have black and grey water combined, where we call it as a stack design. There are various engineering design considering that, but it's a little expensive to work around because there are a lot of provisions that need to work around it for a building. So ideally, designing a separate grey water stack, a separate black water stack works. And the requirement on sustainability says that you have a low fixture. That means you have a double flush, you have a 2 flush requirements happening in a design. Faucets also, that means where the water is coming in should have aerators so that you consume less water. And then basically the definition of all this is either liter per minute, gallons per minute, liter per flush. This is how the engineering definition uses for all the consumption that we got. Okay, so this takes us to the discussion what we are talking about, sustainable engineering definition. Traditionally, what we are doing is we are considering the object or a process. Okay, we focus on the technical issues. We solve the immediate problems. We consider the local context around it and assume that others will deal with the political, ethical and society issues. When we do a sustainable engineering, which is a coordination thought process with architect and engineers working together with the developer's perspective, with the environment into consideration, we convert this approach to consider the whole system in which the object or process is used. We are looking at a whole system now, not as an individual element. We are looking at both the technical and non-technical issues that need to address. We will solve the problem for the infinite future. We are looking at the future, not the present problem. That means if I am straining the energy requirements on the infrastructure, how can I reduce? We consider the global context. That means where the country is also looking in terms of all the developed countries, what is the strain that a developing nation is going to put on the environment. So it's a little outreach. And we acknowledge the needs of interaction with various experts. That means it's not a single thought process driven. Many minds are working together to make it work. Ultimately, it leads to a lifestyle which is sustainable for all of us. So that's what sustainable engineering comes into picture. It's not a new concept. Okay? It's not a new concept, it is their practice in our early days, but we forgot all those things. And we have started doing buildings mimicking or aping the West. Okay, when you see Jaisa Desh, Vaisa Base. So whether it's Rajasthan or whether it is Middle East, we used to wear clothes which is suiting the environment over there. Where I have intense of heat, I am wearing a pagadi which is a turban which is really protecting me from that heat from outside. Whether it's Middle East, I am wearing these clothes, kanduras and stuff like that, which help me to allow me to perspire well and so I can still breathe around. Whether it's extreme weather, I'm in the Eskimo region, I'm utilizing this fur. So buildings used to be designed like that. Over a period, we started making it glass boxes. Now when I start making glass boxes or trapping system within this week, everything changes. So that's the reversal that we would suggest that you as future mind should look into supporting this thought process. That can we reverse it and make it more sustainable. Yes, there will be cases that you cannot avoid air conditioning, but again I'm putting the stress point, consume less. Consume less. So design in such a way that your requirement of air conditioning doesn't come to picture. That means for the environment which you are designing the project, if the building can be spec'd around it, it will allow you to consume less, and that's where the entire discussion comes into picture. So that takes you to the story about net zero. So for net zero, 60% of my thought process is a discussion between the architect and the MEP team. Because if I'm consuming less, if I take 60% of my project power out from a building, and the balance 40% can be done at site. I mean, I have renewable sources. Now, if we see project orientation will give you 5% reduction. Passive design measures in a microclimate, like if you create more water bodies, more vegetation around it, it will reduce 15% of your consumption pattern. Envelope, when we decide about the envelope, the fabric of the building can reduce 25%. Then the systems, the energy system that we place, it's a growth from 5 to 15 to 25 to 15 to 16. So what's not visible here, probably that I'll tell. More about technologies, about how to get it done. So it's about 60%. So over here is what the technologies depend, and over here is more about you as an architect who's planning the building. If you plan the building right by yourself in your early stage, your consumption can come down by 25%. And we as engineers working with your support can reduce the building consumption by 60%. The balance 40% we can depend on the natural resources, which is solar. That's how we will target net zero. Intent is think. If you can think, you will achieve something. concept of net zero is to reach to a level that you can produce what you are consuming. So that's the thought process that we're trying to give a little seed in your mind. So when you see building massing and studies based on your flow pattern, the movement of air, you start orienting the buildings in such a way that it's not, I mean, you definitely know that east and west is going to be the maximum amount of heat that hits your building. So you're trapping the building with a larger mass if your east and west is facing the sun. So generally we say north and south orientation would be the ideal way of doing it. So if you orient your building accordingly, given the landform you have, the challenges will definitely be there based on the landform, but it does help you to come down. Then of course the microclimate strategy that we spoke about, we do analysis to understand whether the air movements is helping you to pick away the heat. Now if we do dense design, the air gets trapped inside. If it doesn't exit out, it is not going to exchange the heat. You are only building more heat stored into the power. So design in such a way that you are able to have air flows in the zones such that you are able to breathe. The microclimate is able to breathe. With that, you are helping reduction in the consumption. Okay, passive designs, like I said, longer axis shall be facing north-south direction. That's the consideration you say. When we have high thermal mass for external wall, that means we have insulated design for high thermal mass design. Biophilic, you have more greens to the building so that it is also working towards reduction. Then we have solar reflective paints on the roofs and terraces, which is reflecting rather than absorbing. Water bodies, that's in the landscape that you create more water bodies. And you create buffer zones. Wherever your buildings are hitting from the external mass, if you're getting a direct heat of sunlight, create that as your buffer zones, not as your actual consuming zone, maybe as your drop-off zones. So by the time you reach your actual points where you are really utilizing, you have less energy that is flowing into the building. So buffer zones are very, very critical. If your massing of the building just increases beyond comparison. So that's something that would come into picture. So like you said, the core of a building, the staircases, they can all be defined towards the east and west side. Toilets can be defined. So all those kind of things. So reduce these kind of consideration and put towards north and south your visions across. South, north. If your vision panels are towards this side, less heat that travels. Okay. We also talk about, as an engineering consultant, we talk about reducing internal loads. Oversizing, overspecking of a space is only defining how much do you want to really run a system. Definition of occupancy per square feet is based on where you sit. In a auditorium setting, we generally consider 10 square feet per person. Right. Now, if this opens up to an office, this will become almost like a 70 square feet per person. But yes, banqueting halls, which is for hotels or for auditoriums, you will consider occupancy at 10. That is given. But if I design an office also for 10 square feet, it is way beyond consumption. If you are stuffing people inside, like we do in BPOs, we have 25 to 30 to 40 square feet per person sitting in a space. It is just stuffing in people. So definition of occupancy in a building is critical. The lighting that you need to design is now very efficient. It cannot be at 1-2 watt per square feet. You can come to very low requirements. The building envelope, that is the heat that comes into the space, considering the engineering that you do, can get reduced to just 1 watt. Equipment power, basically like today in this, we have no equipment other than my laptop running in or a projector running in. That specification is also coming down. So we need to evolve to technologies which are using. And of course, energy efficient equipment, the air handling units, the design would be in such a way that we are going to consume less power and take solar energy as much as you can. That's how we are targeting the production. And you can see air conditioning system designs which are more on radiant cooling possibilities, if possible. Because institution buildings can be easily done with radiant cooling. It need not go with central air conditioning plant rooms. You don't need a 21 degree or a 22 degree Celsius in a room for an institution building. If you can still manage with 27 and 28, which I can still do by running some external water piping in your slab which will absorb the heat, is possible. And particularly in projects which are towards the north or the dry side of the climate of the country, you can easily achieve gradient cooling. But it might be a little difficult into say zones where monsoon or coastal regions are very too much of rains are coming across. But yes, then you resort to air conditioning, but there are various techniques in which you start reducing them. So this is all about how we look into, and then the balance 40% which I said is necessary is either by solar, wind, hydroelectricity, biomass, geothermal. Biomass and geothermal will only work if you have a large site. But if you have a single building, this cannot work because you need space. You need space for biomass, you need space for geothermal. Otherwise, it cannot dissipate, neither absorb. So yes, you can still look at this building, solar, wind and hydroelectricity. Taller the building, the potential of a wind and hydroelectricity becomes much more easier. But solar is available across. You can utilize your terrace, you can utilize offsite renewables also. But like I said, the last two set, the biomass and geothermal, is only applicable when you have large land base. Maybe you are doing a large massing design of housing, you have 50-60 acres of a land. Try utilizing geothermal and biomass as an alternate source. So that's something that would help you in your thought process in plan. So we are also now thinking about net zero beyond. So there is a zero carbon, there is a zero water. That's a little bigger take, but that's where the industry is thinking. It's not just net zero energy. It is also talking about zero carbon, zero water. That means you are generating your own water. So we will talk about it a little bit on the water side also. And zero waste. That means whatever waste you are creating, that is also getting converted into a usable form of energy. So that's where the industry is now going forward. But at least let's try that energy side first and then come to these pluses that we can help on. Okay, now very important that you absorb this picture, right? This is my most favorite picture where I always present it, and to all the young minds, you are the captain of the ship. Hope you can read this, right? The architect is the captain of the ship. This is the building that you are designing. It is going to go through a sea change of climate for the 50+ years that you want to design the building to survive. It will be impacted by various issues. Climate, people, social, political, and it is going to a sea storm. That is what we call as climate change. A ship that reaches to a destination is not always on the clear water. It will go through a lot of issues. Same case with your building. It will go through climate change, but to help you to wade through that climate change and make your building work, we have a marine engineer, which is what MEP consultants or structural consultants are. But we depend on the captain of the ship to lead the thought process. So you need to take accountability in terms of leading a project. Do not say it's a consultant, MEP consultant job in future, it is your problem, you solve it. No, you are the captain. You are the captain of the ship. The architect is supposed to lead the pack, and that's what the responsibility lies, right? So with there's a take on Spider-Man, right? Greater responsibilities or whatever it is. You also need to look into that. So the commitment from your level will also be on those lines, that you have to take more responsibilities of delivering project inclusive of other consultants' inputs. It's a structure for mechanical engineering. But that's your project that goes to the sea storm. Yes, this is what we generally hear from all coordination that we have. Coordination is a pain between an engineer and architect, but it's about to know better in the actual practice. But if we all work together, it is not a pain. That means if you are breaking your system requirements from your day one on your concept design, you understand what is the requirement of various consultants, you table them out and start finding solution. Coordination is not a pain, it's really fun. You will really enjoy the process of a building that gets developed. And first thing is to forget this picture and think, no, it's not a pain, we are going to enjoy the process. The process that your building will reach after 5 years of a design and maybe see a light of the tunnel with a functional usage, and people saying outside, wow, what a development. That pain goes away. It's something that really makes you feel proud of as an engineer, as an architect, as a structural consultant. This perception has to be taken away. So what is the perception that makes work? So what is the question that you really put up? Okay, generally, the question when you start picking up in a design. Okay, as a designer, what are the issues? Open space requirement, because it is governed by your bylaws, the codes that I need to, if I'm making a tall building, I should have minimum 60 meters setback given from this side, that side in consideration. I have the wind pressure, which is the facade impact that comes onto the building. So taller the building, taller the wind pressure, problem comes across. That means I have to design my facade to take care of this wind pressure. Pumping strategies. Smaller the building, lesser the problem. Larger the heights, the taller the building it goes, pick a building for a big. Whether it is structurally driven or mechanically driven will come into picture. The position of a DG location in a commercial building very specifically, where you are doing 100% backup, where power is an issue, you do 100% backup. In commercial urban cities like Mumbai, Bangalore, any city, the expectation of 100% backup power is a must. That means if I consume even a transformer's electrical power, I still will provide 100% backup, because I am not willing to sacrifice even a day, 1 hour or few seconds without power. Because the business will get impacted. Any business get impacted, the revenue of that business will come down. So they are stating requirement that the building should be 100% backup. So when you back up a building with DG, the diesel generator, that's 100% backup. The problem is, where do you locate them? And if you locate them within a building, you've seen some stack that needs to come. That's a stack. It's a flue pipe. The flue pipe comes within a building line and right goes up to the building top. That's a critical design consideration that comes within a tall building. And if I place them outside, which is at a landscape level, then the building looks very eyesore. So there's a big mass of elements sitting out. And you see a tall structure like a chimney, like a structure 30 meters from the side. So visually planning them is very critical. Scalability, so there will be requirements from the client that today I will build only 40 floors. Then I should be able to build 20 floors more. Then there are possibilities. Like you have an opportunity of FSI changing. So if you want to build taller, it is dependent on the government norms. It does give you provisions to scale. So can the building be scalable? The question from an architect to a developer is, do you want the building to be scalable? If you want the building to be scalable, the provisions for services for MEP or structure should also be that. It cannot be one fit and say, now I have to put one more certain system on the top later on. So I would do scalability, staging, how do I build the building? Various construction strategies of staging the problem. Heat rejection device, that means whether you are putting a DX system, a split unit or a central plant room, where are they exiting their heat? Ventilation, that is a toilet extraction. Tall buildings have a bigger problem for toilet extracts, because when you have external wind hitting your property, you are not able to reject the air out. So it will become centrally located, cores will be located. So all this is basically we call as engineered approach to the building service. Again, like I said, if you point out everything, the coordination between architects and MEP engineers or structures will come down. If you list out all this from day one, you will get the answers before you start planning them. This would lead you to considerations of the MEP. So I will just explain what are the considerations now. So all this Ram Katha was to tell you what are the considerations that we need to come. So till now everything fine? Hope you're not sleeping? Right. Thanks. I mean that's a positive sign for me. Then we spent about close to 30-35 minutes, or maybe more than that, 40 minutes discussing the build-up to the story. The build-up is necessary. Right? And then we talk about what it is going to get implemented. So, what are we considering if we are talking about firefighting design? Most important in a building, because the taller a building goes, fire and evacuation strategies are more critical. One life lost is detrimental, not about the project, but a life loss is something which cannot be tolerated. A building may go for an issue, but life should not be lost. So, a firefighting design has to be given the utmost importance. Then the mechanical, the electrical, the plumbing, and the integrated building management system, which we call as the low voltage services, which is basically only a channel of communication between various services. Okay, for the fire service, we divided into firefighting, we call it passive and active. passive is something that should be in your plan as an architect. That means I am not dependent on any external firefighter to come and save me. I have ample time within my space to be safe. I am able to design a smoke-free zone. I am able to design a space where my fire is not coming within my space. I am able to create a space where I am safe till the time somebody comes and pulls me away. So that's your passive. That means your staircases, your codes, that 2-hour rating, 4-hour rating as per National Building Code. This when you're doing your probably you will have this requirement of designing this. And then as an engineering consultant, we really work towards active. That means a fire has occurred, but how do we limit the damage? Fire has occurred. You may not be able to save it, but how do we limit the damage and control it such that it doesn't become a wildfire that the entire building gets engulfed into it. It is a sporadically controlled zone. Active is by coming to know which building, which room, what floor should know that particularly in an auditorium there has been an incident. Then the reaction to that is directly towards an auditorium rather than spreading across the entire set of buildings and find out where is the issue. So that helps by detection system. And then suppression is basically designing for sprinklers or extinguishers. That's just suppression. So that's how it really you when define your firefighting consideration. Now passive, something which is very critical as an architect you may need to provide is all the strategies for your zoning. We call fire compartments. So when you do buildings larger sizes, you have compartments where they define. So there are physical walling of compartments which in which they say this is a zone. For a basement car parking, it's a 3,000 square meter of a zone, which is called as a fire zone. Beyond that, you need one more fire zone. So it goes to various usages. If you see institutional building like this, would need a fire zoning for 800 square meters as against a 3,000 square. So keeps on increasing. This is there in the National Building Code. If you want to look into this very specific, NBC 2016, chapter 4, fire and life safety. Please note down because this is critical. As an architect, therefore, you should know very specific how do you define the zoning, fire zone. National Building Code talks about this very critically. Then we talk about the egress and evacuation strategy, how you are moving out of the building. That speaks about the egress strategy. This is also a requirement from the National Building Code in terms of fire tower arrangement, that you have a fire tower and an elevator which allows the firefighter to come in and pull people out, and then they are able to exit into the protected staircase. These are all fire component designs. The NBC talks about also the strategies about distances, what kind of distances we need to maintain for various travels. That's also an NBC code which you would request that you should go into. Then there are regulatory requirements on a building, like a tall building like this, you need fire extinguishers, you will need hose reels, that is the risers, the wet risers, the hydrants, the automatic sprinkler system, and what is not rated has also been explained in terms of what comes into this. Regulatory requirements of ventilation of staircases is necessary. These are more about passive strategy. I'm just giving you a little idea. And all of this is compliant to National Building Code for various reasons. An example of a building which is this is the staircase. You can see the staircase is designed, and you are trying to figure out the radius in which the people can move in. It's a 45-meter distance is in a sprinklered building. If it's a sprinklered building, it's a 45-meter distance that you can allow from one point to the staircases. So you can see the radius that comes in. Refuge areas are something that are necessary to be planned in terms of accesses, and again defined by the National Building Code, which we need to plan for. Given some experts from the National Building Code. Again, I would request that you go from the National Building Code Fire and Life chapter safety chapter and have a look into it. Some calculation which shows where do you need the refuges. Generally, after 24 meters of height is the first refuge that comes in. After the first refuge, every 15 meters you need the space where people can extract evacuation strategies for it. So a building which is say 27 meters floor, you can see the refuge areas keep on starting from the first 24 meters, and every 3 floors you start refuge areas coming. This refuge area should have access from the main fire lobbies. That's something that it should happen. Okay, I did not not sure whether this works. Fire spread in a small video just to give you an idea about if there is a fire. It's a wireframe model of a building, just giving a little idea about how the fire starts. And this was the core of the building where you have staircase, elevators. If you have a fire, it will first try to see the space where the vertical shafts are getting connected. The smoke will travel to the vertical shafts and then spread to the building. And if the facade is not able to hold, the fire will start going from bottom to top. You can see an elevation from the top. Then the central core, where you have elevators, how the fire will start spreading inside. You can see the population within the cores. The smoke getting filled up. And it is the smoke that kills people. So the passive design that I am able to create more barriers before I can use a core is very critical. Some of the various angles that we are trying to look at. I'm not seeing why it is not visible. Okay, let me try. And then you see the smoke moves away from the building out, and the fire gets carried away from the outer to the upper floors. This is how the spread happens from the occupied to the core, and you can see from the core it will start moving up over a period of time. So that's an idea about how serious we should be designing the core. Okay, just running this little what we spoke of. So all those were a discussion about passive fire. How to design the core in such a way that you are eliminating the travel. Now we talk about active. That is where real provisions comes into picture. When you really look into projects, which is tall buildings, you see you need to create the building design to various zones and zones. If it's a 15-meter tall building, it's one zone. A 45-meter tall building, it is two zones. A building beyond 45 meters, it is three zones. So that's how we start defining the zones in terms of design. So the water flows from one tank to the other and from the other. There's a tank there, it's not visible here, but it should come there. Challenges in fire system. We need to design the boosters, the vertical risers, the trenches, the facades, and all these evacuation aspects into consideration for the fire. Fire alarm system is a critical aspect. We have a lot of IS codes and NBC 2016. I'm not really spending time in that. But if you can go through the NBC codes, it will help you. It gives you idea about what are the provisions that you need to come into picture. NFPA is also National Fire Protection Act, but it's a US code which we will be utilizing for various buildings now. Fire activation device, we have the smoke detectors, the routers, the controlling modules, and then the communication system that needs to go between various buildings. Firefighting consideration for NBC 2016. Provision of a fire tower is a must. We spoke about the fire tower. A fire tower is a staircase, an elevator, and a space which is proven to be pressurized for evacuation. This is a must. Buildings which are getting taller is now getting designed at a 60-meter zones. Any building, there will be 60-meter zoning for fire to be defined. 120 minutes of fire-rated corridors are to be necessary to be provided. Refuge areas are to be provided with sprinklers, extinguisher, fire. The pumps, the firefighting pumps would be at multi-stage, multi-outlet because I will do zones. We spoke about in that. They are needed for reducing valves. Express risers, I mean this is more of a technical. We need to provide additional support risers for various buildings. When you go to residential per se. Buildings that are getting taller, 50, 175, I need storage at the top level also. I need more storage at the top. So I need to provide additional auxiliary tanks. Critical is fire audits get every 2 years. Whether it is getting done, it's a questionable club. I think over a period of time, the municipality is going to make this as a mandate that there has to be a fire audit every 2 years. If it is a building about 200 meters of height, it needs a helicopter landing, helipad to come in terms of. Sorry. Fire detection. That means all the smoke alarm system has to be compliant to the National Building Code. I will just run through this. Now comes the air conditioning. We spoke about the process about air conditioning. This is something that would be helpful to you in your planning because when you air conditioning design, we talk about either centralized or we talk about unitary. Unitary is what you see here. What we have one independent units connected to an outdoor system is unitary. Right? I have an air-cooled VRF or a split units. Centralized system, we call it water-cooled Air cooled, that means you need a plant space. It needs to be put up in a building plan somewhere. Within the building, air cooled system is put outside the building on the terrace, and unitary system generally it's considered as air cooled splits or VRF units. They are unitary system because it's not connected to the building. It is designed for a floor, or it is designed for an apartment. It is designed for one common office. Central plant rooms are designed for a full building to work together, and that's where, if you see, energy-wise savings, highest savings of energy comes from a central plant in terms of operations and cost. That should be the fundamental we are trying to look at into design. So again, when you really do building design, you should analyze the building so that your definition of load calculation is worked out, and then you start going into it. So you do the mapping of the building in such a way you understand which facade is getting heated, and accordingly select the right glass. If you select the right glass, the trap heat is going to be less. The trap heat being less, you will use lesser size of a air conditioning plant. So this is something that would help you in definition in your planning process. You also need to look at the solar radiation of the property. So if I want to utilize a photovoltaic cell, I can use it in my fascia here also. There could be a design where my building can be designed with photovoltaic cells, which I can produce energy for the building. Depending on the orientation, the massing or the radiation that the building needs to address. Most critical problem lies is the placement of high-rise in high-rise buildings. You may keep ODU or in spaces where it's got no air circulation. What happens is the temperatures keep on rising. I'll give you a diagrammatic application. The temperature at the lower level, if it's a tall building, is at the general 35-34 degrees outside. Most important. Elevation of the building is required, but it's not the elevation that keeps the building healthy for over the years. You need the systems to function. So placement of the not be within a core, assuming that you find its own way to design. And then you find issues related to heavy temperatures coming outside, and this is some CFDs that you do on project to understand the placement of the units particularly. Okay, now giving a little idea on your stacking of the building. If it's a commercial building, generally you will have basements. Right? You may have additional floors. It's a mixed-use development. For a property like this, it's a mixed-use development. You have office floors, you have parking, you have retail, and you have basements. So, based on your parking requirements, you may define whether I need to go further down to accommodate that many number of car park, or can I create a parking on above ground, which acts like a buffer. So I have, say, in this particular project, we have, say, two basements, we have a ground floor and then a retail segment, then you have a parking and then the offices. The taller the building it comes, you need to create some services and refuge floors. So this stacking is something that comes into your design consideration. The taller the building it comes. But if you have a land mass available, you are spreading on a floor, not a necessity, you can spread it. But on a mixed-use development, the consideration goes maximum for services, that how many stack can you create. So this is something, just an idea for you to really understand the stack. Build heights, I will leave it, it's more technical, I will leave away from this now. But as the building gets taller, like I spoke to you, you have a wind impact that comes from the building. The elevator that needs to move from bottom to top, even that should be designed with some venting strategies, because it's like a piston effect. You have a large piston and somebody is moving with a piston. There's a large amount of air volume that keeps on pushing towards the core. It should be allowed to exit out, and that planning is very, very critical in a tall building, because if that doesn't allow, it is going to be detrimental for your core design. You need to have some openings for that to vent out that extra air that needs to put out. So that the elevator movement is very critical to be looked into when you are designing taller buildings. So I'm just putting up what are the challenges. You have several staircases to be pressurized. You have toilet extraction to be done, kitchen exhaust to be done, mechanical ventilation of heat rejection. You also look at shading of building. And in projects where it is closer towards the sea, the condensation of the property becomes a very critical analysis. Suddenly you do a big glass building and you're not able to see outside because it's all condensed. And that's where your intermittent field from in to out is also changed. So it's very important to design how much should be your window wall ratio when you're doing this kind of buildings also. Just a little pointers to think. Okay, on the electrical services, we are talking about giving you a little idea about what are the type of transformers. So basically, in a property, you have two set of transformers. We call it oil type and a dry type. In your property, in your college, when you probably would have come, if you take an opportunity when you're going outside, you will see transformers outside. Okay, and they are called oil type. Oil type transformer cannot be placed within a building. Very critical to understand. An oil type transformer cannot be placed within the building. It should have a mother earth outside because it is having oil to cool the system. So if there is an oil within this, it is explosive material, and if that explodes, it is going to impact the building also. That's the reason why the regulation says you have to place them outside. So when you place the transformers, the electrical transformers within the building, we use them as a dry type. The dry type transformers are going within the building. Some examples about what plus and minus for oil and dry type is. I'll skip this, it's not a necessity for you. But you need to understand metering strategies. Because when you do design for building, what are the various meterings? Because that's where your rooms will come into picture. What rooms are needed where? So basically we define it into three metering strategies. Metering is high tension metering, low tension metering, and a combination of high tension and low tension metering. If I was doing a simple residential meter building, I would be designing this property for a LT metering, low tension, for a residential. That means I have small meters in a electrical room. I am getting my feed from outside from a supply company. I am only putting meters. I am not putting in transformers inside. Much more simpler for you. You don't need to give a space for transformers. But when you come shift from a residential development to a commercial development, which is a mall or a hotel or a hospital or something else, you will go into this category. So it's called HT metering. HT metering would need transformers to be within the building or outside the building. That decision can be taken as per your design call, what space you have outside, what space you have inside. If you are outside, you can use oil-cooled transformers. If you are inside, you will use the normal transformers. Now we can be single user, like if I am a hotel operator, for me I am a single user, I am consuming the entire power, so I become a single user. But if I become that means I have various retailers, malls, commercial office, they come at multiple users. They come to a different branch. So if I say single user, like hotel, single occupant, IES college would be a single user, right? But within that, if you give some spaces to somebody else, they'll become multiple users. So they can use separate. So we do HT metering, LT metering, we also do combination, wherein the utility of the building, that is your plant rooms, your plumbing system, your sewage treatment plant are fed from a common HT site that we do for malls, IT parks and commercials. And for smaller offices, you directly will give power from the supply. So this will actually define the usage and number of rooms that your property would come. And this will get further optimized in the design. But this is the base in which you start thinking about building in terms of electricity. Now when you go to a high-rise building, because high-rise is always the biggest challenge, we need to look at whether the building is serviced by cables or there's a system called a bus bar. So we give a power in bus bars, and from the bus bar we tap into every floor and then the power goes to the relay system. If you do cable per flat, you can imagine the number of cables that will come in a building which is 300, 400 flats. That many number of cables will start traveling from bottom to top and start reaching. More the number, the more the problem with the fire possibility on a building. So bus bars are designed in such a way, they are sandwiched, they are insulated, it will not create any short circuit. But you can tap off for 4 floors in a one single floor and you start utilizing the design. Earthing system of a building is the most critical design that goes with the rebars now. The structural designer will give you an external rebar, and that earthing is getting connected so that any short circuit that happens within your building, your neutral gets connected and you are able to pull them out of the building without you getting the electrical shocks. Then sizing the transformer. So these challenges are that we need to address as we move forward. Now we come to public health. The various type is design wise. When you say public health, basically how the water systems are designed. So smaller building, we can do a single booster, bottom to top, or we pump the water from roof to the top, and from top we start coming down, and we do a gravity. So this is basically mechanical pumping. This is partial mechanical, and then coming by gravity, consumes less amount of power, preferred for a residential design, or we do series of multiple connections. When I show a stacking of those service floors and rooms, I would have done something like this. I would have series of multiple pumping happening. So a series which will take care of gear towards the various floors, and next set for the next floors. This is done in Burj Khalifa, you can call that. A building which is 828 meter tall building, it cannot be just done with one single riser. It will be done with multiple ways of managing it. So I would say a tall building which is more than 300, 350 will be done like that. A building which is a residential will be done like this. Or it can be done with smaller floors, second set of floors, next set of floors with various stacks. It consumes more space but is effectively able to manage. So if I was to do a scalability of a building, so I would build another 20 floors later, I would design a building which is simpler like this. I have for every zone that comes up in a building, individual pumping that can be utilized and managed. So similar concept that I have tanks also and then pumps which can feed. So it's a combination. We'll have to take a call based on how the design we'll have to think about. But these systems are available and they are all analyzed and then you can utilize them on the project in terms of how the pumping is done. So the recommended thought process. So you can see what we're doing is you pump, that's your water tank storage. You have one set of tank, you start pumping them to the topmost level. Okay. The next set of overtake comes down and then next set comes in and you start consuming. So basically you are trying to give a little break into various zones. We spoke about during the plumbing design about the double stack, the soil and waste. Designs are now coming up where we can club them together. It's an expensive affair. The project can get built in. It will give you more space for your leasable carpet areas because you are combining one single riser with a specific design that comes into consideration. But you have to be careful about this design. It's about the engineering is not an IS code, it's on European code, so we have to design according to the European standards of design. But it does give you space consideration when you do a stack design. Fortunately, you're not seeing the best picture that's going. Okay, let's understand this various source. You sum the entire thought process of consumption of water and a treatment into this single plan. Right? Now, this is called as water balance chart. In every project, you should have a water balance chart. How much water are you consuming? From where are you getting it? And where are you reusing it? So, I'll just run you through my cursor just to give you an idea about it. So you get a municipal source of water. That water is divided into a domestic consumption. The domestic consumption will go to, after your consumption, to your units, will go into a wastewater generator. So we spoke about soil and the waste. The soil, that is basically your black water is your flushing. We call it as a flushing line. Anything that you are able to be in touch with is called as domestic. Anything that you are not touching and it is getting into your usage point is called flushing. Domestic and flushing. So the domestic water comes from the municipality source. That means your potable water. Your flushing water comes from a treated source. That is your sewage treatment plant. I'll explain what happens. So you get a certain percentage of water from domestic into your total water. Your flushing comes back, usage. We go to the wastewater. It goes to the sewage treatment plant. The sewage treatment plant is able to recover 90% of this water and able to give back to the system. That means you can reuse this water. This 90% of water in a commercial building is used for air conditioning systems, cooling towers, and for landscaping. When you have landscape, you need water. You cannot consume municipal water for landscape. That's a requirement from the government also. You have to put a sewage treatment plant where you can recycle this. So the sewage treatment plant is then utilizing these processes where we have primary settling, secondary settling, and tertiary, where we clean the water from various angles, we ozonize them, we do a UV treatment, and the water is good for you, not for potable consumption, but for flushing, for cooling towers, and for landscape. That's how this entire balance of a chart happens, and you call it as a zero liquid discharge. That means you are not again straining the municipal source for pushing your building services outside. Within your building, you are creating your own treatment plants. That's how it is. Then we talk about the challenges within the building for high rises, which is when n numbers that you have to think when a building becomes tall. It will come with the issues of drainage, the basement dewatering, because the more you go excavating below, you will have the groundwater coming up. So that's called a basement dewatering. So you need to be careful how close is the building towards the sea or to the water, groundwater importance. That's how you will take a decision about how many basements you want to create. So you may create just one basement and make all the parking level at the top, or you may create 2 or 3, subjective to the groundwater that's available. We need to take care of vertical stacking. The rainwater harvesting is the most critical requirement on every buildings that we design now. You need to store minimum 2 days of a storage of your catchment of the roof. So that's a requirement from the municipality. A 2-day storage of the roof catchment area for 100 mm cubic meter of water rainfall that is issued. Hot water systems become into picture. Domestic hot water return pumps. When the building becomes taller, you need to also put reducing walls, and the solid waste management. When we say solid waste management, basically it's your garbage movement. Your garbage movement means you need to have an additional set of service elevators, because service elevators are needed for you to pull them out. You cannot go from a common passenger elevator. You need to have an additional set of service elevators for getting a solid waste management reaching to a point where it can be collected by the municipality. Okay, so let's sum it up into space planning. Whatever I have spoken about in a diagrammatic fashion, just trying to explain you if this is a building for you, a commercial building. So you can see at the lowest level, that's your basement 3, assuming that I have 3 basements, I am able to put the air conditioning plant room in my lowest basement. The requirement from the code requirement says that the fire water tank, the fire storage, the fire pump room should not be less than basement 1. So the placement of the fire pump room is at basement 1. Okay. I can put a domestic water tank at basement 2 and basement 3, not a problem. I will put my electrical substations and panel not lower than basement 1, but preferably be at ground floor. The intention should be, if you can get a space at ground floor for electricals, place them at your ground floor. Do not place them, if not possible, maximum basement 1, but nothing less than basement 1. Then you see the requirement of sewage treatment plant. Again, the consideration in Maharashtra, if you are designing a building, the STPs has to be in basement 1 maximum, and they require natural ventilation. They want it to be naturally ventilated. 40% of your space should be naturally ventilated. And then if you see, you have independent meter rooms at every floor, and the air conditioning plant room which is sitting at the basement would reject the heat to cooling towers, maybe sitting at your terrace level. So your terrace will have cooling towers depending on the building height, and of course your building top will have your fire tank, water tanks and stuff. So this is summing up the positioning of the systems in a commercial building. What changes in a residential building? Everything remains the same. Your air conditioning plant room is moved away, because you don't have a central air conditioning plant room in a residential building. You need to plan these guys, a space for the ODUs, the outdoor units. So what happens in the residential building? You need a breathing facade, a facade which will be able to breathe. It cannot be a massing of just glass or concrete. You need to have space for doers. So the visualization of a residential building and a visualization of a commercial building changes completely. Commercial building, you may create more of a glass look and feel, but residential building, you need to create a more breathable facade, because everything else being generally the same. The provision for STP, the provision for water tank, the fire, the change is basically your air conditioning concepts. You don't put a centrally air conditioning plant room. You will put for spaces to put ODUs and internal designs to give you solutions for this. And you need additional meter rooms for every single usage. So this being said, what I'll do is I'll just take you to a little quick run of some of our existing idea about how they look and feel. Another 5 minutes and I will be open for the house to discuss. And your torture will be over. Okay. This is an existing building just to give an idea of space that we can look into. One of the commercial building that we were designing for. Where did we place them as a commercial building? We placed the HVAC plant rooms at basement level 1, what we spoke about in your schematic diagrams. We placed the chiller plant room at basement 1, we have ventilation fan rooms for that particular area. Then there is HU rooms at every typical level. Then what are the other things that were terrace for a commercial building? Air-cooled chillers, treated fresh air HU. This is the air that comes into the building for you to breathe. Indoor air quality is something that we will treat at one point and push the air at one point. Not that we start pulling air from everywhere from the building side. We pull it from the terrace, we treat them and put it inside. The cooling towers and the fire and life safety requirement of pressurization. You have to keep the building under pressure so that smoke doesn't come in. So that's a pressurizing fan. Just to give you an idea about how the space planning looks like. Now this is a basement that is probably equal to 80,000 square feet. Just a scale, just to give you an idea. The red zone that you see, this is the core, where the building starts vertically going up. Towards the extreme end, basement 1, we have a finishing plant room where you have chillers, 1, 2, 3, and a set of pumps to make things work. Right? So I'm not able to see this height, I mean, this is different, you can feel over here. In terms of ventilations of the basement, you need to ventilate the plant room 1 and 2. So there is ventilation. During fire, you have to extract this and it moves away. During fire, it will extract. So there are 2 fan rooms that you have to provide for fan rooms for ventilation that comes in. In the typical floor, the resolution is somewhere getting literally disturbed. Okay, I'll show you something else. Okay, on the terrace, on the same mass of the building, you can see cooling towers, you can see air-cooled chillers, you can see fans. So the entire terrace gets populated by mechanical service on a commercial building, definitely. On a residential it is less, you just have fans and stuff, but for a commercial building, your entire space gets completely utilized for services. Okay, not able to show you the best pictures. Okay, for the electricals, okay, what comes out the ground level? You have a HT panel, you have a metering room, you have a substation, that is basically your transformers. Most important point is a fire command center. Every building, whether it's commercial, school, colleges, or residential, should have a fire command center. A fire command center is a zone where the entire low voltage, the CCTV, the fire and smoke management, the smoke detection is coming to a panel, and somebody from the civil defense, that's your firefighters, they're able to reach to that and able to address at what location the problem is happening. So this has to be placed at ground floor. It does consume a space, a premium space of your ground floor, but it is a necessity to provide that at ground floor. And if it's a commercial building, we also have a diesel storage outside, if it's a commercial building. For a residential building, this may not come. Other things will all come, but it may not come. The diesel storage. Then you have electrical plant rooms, you have panel rooms, you have PG rooms, they are 100% backup. The UPS basically giving power to all your general lighting for your evacuation lighting, and you have electrical rooms at all the office floors. Oh, it's not visible. Just to give a little scale, if you were to visualize that section at my basement 1, okay, in terms of fire, whatever we spoke in the basement level, just give you an idea about. Yes, if you see the building line, we have fire and water tanks in the basement 1. Some definition of how that operation happens within the fire, but it is a basement 1 generally. I prefer to get basement 1 only considering the firefighters requirement. The sewage treatment plant onto the extreme corner of the property uses. OWC, the organic waste composter, that means all the garbage will come and get stored here, and from there it is picked out. So you need a space to get all this aligned into all your space. And your flushing tank, post your sewage treatment plant, you need a storage for your flushing to happen. That's what is in the corner. A STP again, it's a double height, because basement 1 and basement 2, because it needs a minimum. See, in terms of height, generally plant rooms can work within 4.5 to 5 meters. But for a sewage treatment plant, it needs a larger height. It creates about 7 to 8 meters. So that is a consideration that you should have. An 8 meter to 7 meter space as a height for plant room for sewage treatment. Otherwise, all plant rooms can work within 4.5 to 5 meters in a commercial usage. On the site services, you have space for a gas bank, you have space for the alarm check wall, rainwater harvesting externally, this is for external. Just to give you an idea about what comes with the external. And at the terrace level, you have basically all tanks. Now, if you see the core, the central core of a commercial building, I'm assuming I'm dividing this building into 4 offices. 1 office, 2 office, 3rd office, 4 office. The taller the building, the core will get defined with respect to your elevating strategy. Your elevators will not be absolutely openable for all. We'll design the elevators for low zone and a high zone. So midway up to the building, we design this as a low zone. So you have elevators feeding low zone. So if somebody needs to reach to the topmost levels at 30th and 40th floor, he is going to come to this bank of elevators, not at the second bank of elevators. Because the low zone elevators will not stop at the lower zone, so that you are able to cover the distances on a larger way. So we have a high zone elevator, low zone elevator. You see the HU rooms, 1 HU, 2 HU. The shaft that's connected is HU, generally about 1 meter wide length. Then you have the toilets within the core. So you have a male, female toilet, a central plumbing shaft, which again, all shaft we would recommend should be about 1 meter wide, so that when you're putting a services, you're able to access them. So this central zone is basically your shafts. Then your low voltage, electrical and risers. So we have basically 2 electrical rooms, and then other services that comes into picture. So the central core, and you see the rest of the space is all usable office, which does not have MEP services. All within the core. Operations would happen from within the core. People will access all these areas and then get back into the service core and disturbing the office operations. So planning of these are very critical in terms of how they look and feel. So they little expanded in terms of what we discussed. We have HU rooms, the periphery which can do air conditioning flows on either side, the HVAC shaft, which will give you a fresh air, the riser, chill water network, the toilet exhaust, the plumbing shaft, which is taking care of the male and female toilets, which is about 1 meter tall. You have an access to this, and that access is able to service the requirements. And you see the electrical, see the rendering. We didn't work it out to see how it looks like. So when we work, we will work out with 3D model. When you see going forward, we will also go to Revit, right? In future, I mean, when you come here on Revit, in BIM, like this. So BIM is basically a platform in which services we use the Revit as the tool to work, and BIM is basically a sort of integration of an architectural design, a services design, and a structural design. So the architectural wireframe model gives us the space, and we modulate our Revit service into space. So the air conditioning plant which you saw is with these units, and you see how the services start running into the core. Defining the height of that basement will be subjected to how these big services are to reach to the core. You need to give a minimum fire clearance of 2.4 meters of any driveway. So defining the height of a basement is subjective to how the services are reaching in the course. So if you see the air conditioning plant room here, we have the DG sets there, the LT panel, electrical panels. The DG set will come with the flue pipe, which I spoke about their stack issues. The flue pipe will come to the core, and within the core they start reaching to the building top. And that's how it will start looking into the picture. Some angles, various angles. Again, we have to just flip the angle. This is the air conditioning plant room, electrical panel room, so DG set. And this is a central core. So you can see the elevator banks for low zone, the elevator banks for high zone, and the services that comes in and out, and the staircase that fits within these spaces. Just to give you a little more ideas about these. That's it. I think whatever I could summarize is what we have here. Hope it is too much to digest, but what we thought is in 1 hour. What I can give you back, I will share you this PPTs, so it will be good for you to maybe use it, circulate within the team. So that's the experience that we have in giving you a little much. Definitely the challenge is for you when you go into the actual industry to work will be different. But I said you are the captain of the ship. You need to take all those problems with you and move forward with that we say, the zeal and enthusiasm of solving a problem rather than considering a problem as a problem. So that's a challenge that you will take from the future and your future minds, and hoping that the future mind will deliver sustainable buildings with the help of all other stakeholders. I end my presentation over here. Any questions? Now we are open for the questions. Hope it has been not that difficult for all of you to absorb. So hope it is given a little point to think about, right? Yes. Any questions? They're already exhausted.
Any questions?
Yeah, we can grasp it on its full soon. We can ponder a bit and you can come up with your questions.
Some question, I think most of it.
Yeah, please.
Firefighting shaft size, I think you have covered.
Yes.
Minimum weight has to be 1.
So generally firefighting per se, if you put pipes within the space, is we need 900 by 1.2 meters as a standard riser size, in which you put a hose reel and you have the risers, pipe and all. But that's the minimum size. And for every 1000 square meter of area, you need one riser. That is also very important to understand. For every 1000 square meter of a usage, you need one riser. So if you have say 4000 square meter, you need 4 risers minimum. And the placement of the risers should be such that they are able to take a 45-meter length to the last capturing the property. So that's also criteria when you really look into placement of fire risers. So yes. And any shaft, if you are designing, would be with a minimum 1 meter, because what happens is when we take a 1 meter shaft, some service will go towards the either sides of the shaft. So you have a 200 mm or say piping, next side 200 mm. Then you are getting an array of 600 mm to go and work service them. If you put a shaft compressed, the workmanship of our country is not that good. You need to work for the workmanship. The workmanship is not that great in our country, unfortunately. That we put a service and we fit and forget it. We cannot design. Europeans go buildings where they can fit and forget, because they are ready to invest in that kind of material. And the quality of workmanship is different. Our designing would be good, but if you cannot execute it right, it's of no use. So we need to work for the assuming that there is going to be a fault in the system, which can be serviced. So any shaft you design should be a minimum 1 meter wide, which gives you minimum clearance of 600 when a person is standing and trying to work around this space. Yes, it might eat your entire consumption. So if you, for any plant room number, in terms of you take a FSI of say 3 lakh square feet of a development, you need a plant room which is close to 8% of that area as a MEP plant rooms, 8%. For all additional shaft and riser, you may add another 3 to 4%. So practically overall, generally between 10 to 12% is the space that an MEP service within a building gets covered within the space. It becomes more complex, it becomes like a hotel, hospital, because there are a lot of services that come into it. If you go to residential, probably 10 or 12% gets reduced to 7 to 8% because you're not doing a central air conditioning plant room. You're reducing some amount of services. So at an average level, you can say between 8 to 12% is the space that is consumed within your built-up area for services. In a rough number. That's the kind of a area that we use. Yes. Correct.
They are always getting confused with the pressurization. They feel that pressurization shaft has to be bigger. It has to be as small as possible.
It can be as small as possible. It again depends on how many how many steps it is going to cover. And we consider 2 doors to be open for the calculation. And there are leakages for number of doors. So the taller the building, you might say that the space increases. Life safety space increases when the building becomes taller because the number of egress doors are increasing. The number of egress doors adds up to more leakages. That leakages get added on to the size. But on an average, they say about 1000 CFM per landing is the consideration. Accordingly, say you have 10 floors, 10,000 CFM, 20 floors, 20,000 CFM. That's all it happens.
AC system different because they have for the 5th year. They have a school project, they have a hotel project, and they have multi mixed use.
I think I will.
What kind of air conditioning system should they have adopted? Maybe I think chiller and beam system for the not now, but maybe later.
So I'll give you, sorry, I'll just explain you now. Chilled beam system is we call a radiant cooling. It's a good system when you do projects outside a coastal zone. Projects outside a coastal zone. Reason because when you take chilled beam can be done two technologies. I can take the general water from a cooling tower as a natural water, which is let's say 30-35 degrees. Put the water into a cooling loop, but then the effective temperature is say maybe 28-29, not 23-24. If I do a chilled beam with a air conditioning plant, the problem is that the space becomes almost sort of a subcooling zone. The condensation issue becomes a bigger system. So chilled beam system over a period has been used in the north, wide belt, in the dry climate. It has been used in Pune, areas which are outside the zones of coastal, where humidity becomes a bigger part. Because if you see now, during the rains of July and August, our humidity is about 95%. Come water may, if you come through the concrete structure, it comes in. And this humidity will start getting into condensation. So the fact that we will be using chilled beams is majorly towards projects north or dry climates, say dry generally climate. Now the definition between a central plant and a unitary system is also dependent on the size of the development. So when we say hotels, when we do say 100-room hotel or 50-room hotel, we can define with small unitary. Ultimately, you are getting what returns on the very critical design. We can do a hotel for a BRF design, but it becomes a larger 150 rooms, 200 rooms, 300 keys. Then we do a central plant design. Same case for a commercial property also. But definitely for residential, nobody in this country is designing. When you do a central plant, you are owning quite a amount of operational charges under the development. Because if you do a central plant, you have to, and if you say right, you cannot cut it. So for residential, you always plan a breathable facade where you can put this ODUs outside and you have this kind of design. It could be any of the internal design. But a breathable facade that's sitting outside where you start extending the heat. So for residential, for a small property, say lakhs, 2 lakh square feet, BRFs or split unit design can always work. But the differential is that the larger the development, in terms of say maybe 2 lakh, 3 lakh, 4 lakh, 5 lakh, larger the development, the more inclination towards going to a central plant design, an air conditioning system sitting in the basement. Now, if a basement plant, you should not look at a water cooling system, because if you do not get water for the cooling tower, then how do you do a water cool system? Because you will not get water from the municipality for the cooling towers. So it also depends on what is the amount of sewage the building can generate. So if I do a data center, for a discussion, a data center consumes the maximum amount of air conditioning, but it has got only 10 people operating a building. For a 5 lakh square feet of data center, the people that operate a building is only 10 numbers. What does a 10 number of people generate sewage? It's just 1,300 liters in a day. It's nothing. So data center air conditioning would still be central air conditioning, but it's an air cooled system, not a water. It is not having cooling towers, because I'm not getting my process water from the system. So I guess this iteration of plus and minus checkpoints are very necessary to find out how do we define which system. Larger the size, and if it is generating large amount of volume of water within its in-house consumption, you should look for a central plant water pool. If you are going to smaller definitions of properties less than the lakh, less than 2 lakh square feet, air cooled system, maybe unitary, maybe BRF can be a part of it. But generally the space requirements keep on increasing if you have central plant, so 2% to 3% keeps on adding. But a rough rule here, 8 to 12% is the overall building requirement, and it comes down by 3 to 4% if you take away a central plant. That's the kind of funda that we use. Yeah, anything? From their minds? Too much to palate, is it? Maybe that's how it happens. But I would share this maybe. Yes. I'll be open for any inputs or questions later on also. You can reach me out to Sooraj Nair. You can send that and then we can respond back. hope you had some takeaways from this discussion and might open up some of your points to discuss, points to ponder. Thank you for your time. Thank you for bearing with me and giving me the opportunity. Thank you so much.
Thank you, sir.
This was my
Thank you everyone. Please take a break and join Lens on time.